my name is Julia Wichlatz and I'm going to present to you today the paper Applying Monte Carlo Tree Search in Hierarchical Planning. I wrote this paper together with Daniel Höller, Alvaro Torralba and Jörg Hoffmann. This here is Steve. Steve very much wants to have such a nice house here, but Steve is not intelligent enough to build this house by himself. That's where we come in. We want to explain to Steve how to build such a wonderful house. And to do this, we will use hierarchical planning, because hierarchical planning lends itself naturally to use the innate hierarchies of this house here, for example, to help guide the search towards the solution. So let's have a look at hierarchical planning. It's rather similar to classical planning in the aspect that it has a state, that's the set of propositional facts, and it has what's here called primitive tasks that replace actions from classical planning. So we have a precondition and an effect, and this effect here changes the world actively. But what's special about hierarchical planning is that we also have something called tasks and not just these actions. And these tasks are also used in our search. So whenever we encounter a task that's non-primitive, we will check what methods exist to decompose this task here into different things. So if we take a build wall task, we might be able to use this build wall method to decompose it. If the precondition here is applicable, we can then decompose the task into these two new tasks here, for example, into a build row and a build wall with a smaller height. So in effect, this build wall task here will be replaced by these two new tasks. You can see that there's a nice little arrow connecting the two of them. That's because we're considering totally ordered hierarchical planning, which means that between these two tasks here, there's an ordering which says that the first task has to be dealt with before we look at the other one. So we can't try to decompose build wall until we finish decomposing the build row task. And we could also use a different build wall method if the precondition is applicable to take care of a build wall task, for example by simply replacing it with a single build row task, or we could even use a method to decompose a task into a primitive task that can then be executed in our world. Here it might be strange to have like a build wall primitive action, but in our setting we are considering instruction giving, so this here would correspond to telling Steve to build a wall and not actually magically put all of the blocks in place. So now we have a way to decompose this wonderful house into some task that we can then give to our planner to solve. But there's a little problem of this task here having 6 parameters, which can be numerical, and so this means we have a very large object space, and if we do this we will ground ourselves to death. So instead of trying to figure out how we could improve the grounding for this very specific domain, we simply throw the grounding away and use a lifted planner instead. Specifically shop, or even more specifically JShop, the Java version of shop, since this will integrate better with our overall system. JShop now has the disadvantage that it is lifted and can therefore not make use of any heuristics, because there simply are no lifted hierarchical planning heuristics, basically. There are some lifted heuristics in classical planning, but they are not directly applicable to hierarchical planning. So instead, JShop simply uses an uninformed depth-first search. But for our purpose, this is not good enough, so we have a look at Monte Carlo tree search. Monte Carlo tree search, we have one state in the beginning, then we start what's called a random rollout. We basically just check which are the children, we pick one at random, the left one in this case. So we continue this process until we found some solution, and can then use this cost here we found to backpropagate all the way back up the tree and put this first search node here into our tree also. So when we have nodes in our tree, we will try to make informed decision and not simply random ones. But here we can see that we can't really make an informed decision because we have not discovered what's on the right side here, so we can't make an informed decision of going or not going there. So we simply say we want to visit this and start a random rollout down here. We can see, okay, we have a cost of 10 found in this subtree, so let's do the same thing, backpropagate, and now we have 2 costs here, so technically we can make an informed decision. At first you might think, okay, let's exploit this better cost here, because down there might be some solution that's even better than this cost 10 compared to this rather bad solution. But this is a very biased decision, because it could simply be that here very far down the road we took one bad decision, but if we took another one we would have found an even better solution. So instead of just simply exploiting the costs we found once, we use some system of counting the visits to a node to also factor in some exploration of the general state space. And to balance these two concepts of exploiting a good cost and exploring new parts of the state space, we use the UCT formula, in our case with an exploration factor of square root of 2. So we did some experimentation and we found this generally used parameter to be very useful in our settings. So we simply went ahead and implemented a very basic version of MCTS and JShop and ran some experiments to evaluate this. These are very, very many numbers, but the interesting ones are down here, which clearly state that JShop soundly outperforms our MCTS approach. At this point we could have said, well, bad luck, let's try something else. But we did not want to give up on this notion of having some informed JShop search, and instead looked at how we could improve this search. And for this we looked at the innate things that hierarchical planning has to offer, and one of those things is that due to the hierarchy we sometimes run into chains of nodes with only a single child, which especially in Monte Carlo tree search are rather bad because they slow down our search, and we would have to put all of these things here as a search node in our tree, which would slow down things considerably. So instead of simply taking all of these and putting them into our search, we went ahead and adapted the method that the grounding hierarchical planners use in the pre-processing and simply discard these single child nodes. But since we do not do any grounding, we have to do this on the fly during the search. So basically whenever we encounter a single node child, we throw these away, and only at a point of decision where we can choose between multiple options, we put these nodes as the children of the previous node. If we adapt this notion into Monte Carlo tree search, we can see that there is a slight improvement. It's not very significant, but we're going in the right direction. So we continued on looking and found that hierarchical planning is also a very deterministic setting. So this might not be very surprising to you, but Monte Carlo tree search is commonly used in probabilistic planning, which means that if we reach a goal node in probabilistic planning, this cost here might still change because of some decisions we make during the search. So it could technically be the case that if we visit the same goal node multiple times, that it has different costs. But for us this is not the case. So we don't really want to visit a goal node again, because this cost of 15, for example here, will never change. So instead we went ahead and said, okay, let's mark all of these nodes that we have clearly fully explored as such as fully explored. And also propagate this to the parents to say, okay, if all of my children are fully explored, then I'm fully explored. But to do this, we will have to save all of our random rollouts, because otherwise we can't remember which nodes we have seen before. This is not typically done in Monte Carlo tree search because it can become very taxing on the memory limit, but for us this was not a limiting factor. So in fact we can observe quite a good improvement in coverage if we use this node caching combined with the eliminating single child nodes, of having 30 more solved instances. But we're still lacking behind JShop. So let's continue on, and this time we decided to look the other way at what makes JShop so efficient apparently in this task. And the answer is depth first search. In Monte Carlo tree search, if we encounter a dead end, we will just take this information of, okay, we have found a dead end and the cost is basically infinity, and propagate it back all of the way to the top task. And if this is the first run, basically, this is very bad for us because we did not gain any information that could help us guide the search, and instead are still stuck with a blind random depth first search. But compared to like a normal depth first search, which when it encounters a dead end will backtrack to the parent and then continue on searching down the other subtree for a solution, we do not do this in Monte Carlo tree search. But we did not find a reason why we shouldn't do this, especially in the first run where it's so bad if we encounter a dead end. So we simply went ahead and included this notion of backtracking in case of dead end, and could greatly improve our coverage to now 300 instances, soundly above the JSHOP coverage. But if we wanted to look again at our example of us wanting to explain this house to Steve, we don't simply want any plan. For example, we could decide, okay, let's start out by explaining to him how to build a roof. But this might confuse poor Steve very much so, because he has nothing to put this roof on. So instead we want the notion of finding good plans, which means low-cost plans. So we also introduced the notion of branch and bound pruning, which simply states if we have found a plan previously, we record this cost as the best cost found so far, and every time during a search, when we encounter a node with a cost that is already higher, this can be like a partial plan, it does not have to be a goal node, we will simply cut off the search at this point and declare this a dead end and backtrack this information. And using this branch and bound pruning, for fairness, also implemented into JSHOP, not only into our Monte Carlo tree search. And comparing the costs found by JSHOP to our costs found, we can see that the MCTS approach has much better results in most of the cases compared to JSHOP. We are outperformed in some special cases, but in the majority we are at least as good or even better than JSHOP. So we also wanted to go ahead and compare ourselves to some other hierarchical planners to not just say, look, we outperform this one kind of out-of-date planner. So we went ahead and looked at Panda, which is an up-to-date hierarchical planner that uses grounding. So to implement Monte Carlo tree search into Panda, we looked at what makes Panda special, and this is, instead of using these random rollouts, we can simply rely on heuristic estimates, as this is grounded and we have heuristic concepts for grounded planners. This idea of using a Monte Carlo tree search-like approach, but instead using heuristics estimates, was discovered by Keller and Helmert, and it's called a trial-based heuristic tree search. We only implemented this into Panda. With that, we ran some evaluations. This is just a standard time scale, and over here we have like the number of solved instances. And with this, we can see that these two red lines here, that are the MCTS configurations, are clearly on par with this blue line, that's the standard Panda implementation, but are still outperformed by the set-based one. Which is a bit sad, but at least we are comparable to other approaches. And what might be interesting is that we have this value of exploration of 1.7, which clearly outperforms the lower value of 0.6, which suggests that like the general root of 2 factor is also like a good idea for this kind of implementation. So let's give a short summary. We went ahead and implemented Monte Carlo tree search in JSHOP and found that the basic Monte Carlo tree search is still outperformed soundly by the simple depth first search that JSHOP does. But instead of simply giving up, we went ahead and looked at some easy improvements we could build into our Monte Carlo tree search to have a better coverage than JSHOP, and also a better result in minimizing the costs of our plans and finding good plans, not just any plans. And if we implement an MCTS approach into a grounded planner, we can see that we are still up to the we are still comparable to other grounded HDR planners. Thank you very much for your attention.
Hi everyone, I'm Keisuke Otaki. Today, I'll explain our recent work. So we are studying a path planning problem class called Cooperative Path Planning. Let us see the first figure. The input of the problem is set of requests on a graph. The output is the set of paths that minimize some objective function. For example, we try to minimize the total travel cost of all requests. In the figure, we draw two sets of paths. One is shortest paths and the other is cooperative paths. The cooperation here is represented by sharing subpaths by request. Our motivation is to build an efficient solver to build cooperative paths for this problem class. We have two key features of our problem. The first one is we often take non-shortest paths because of the discount effect of the cooperation. For example, the minimum cost of the blue request is the shortest path. However, we need to evaluate the cooperation, the blue and green, to reduce the total travel cost. The second one is that we assume vehicle types and some order of discount effects. For example, we have a vehicle and a UAV, and we have an order of discount effects like this. We prefer to select the cooperation among vehicles if possible to reduce the total travel cost. For this problem class, we know that small instances can be optimally solved by modern IP solvers. However, the behavior of using IP solvers was not analyzed in detail. In addition, we have no scalable solvers, so we are now studying this problem class, and this talk presents some experimental results. In this slide, we show two experimental results using IP solvers. First, we evaluate the capacity constraint. Let us see the figure. We evaluate the travel cost of three vehicles. They travel together from A to B. The parameter Q works as follows. When evaluating total cost, if Q is 1, a vehicle can cooperate with another one vehicle. Therefore, the three vehicles are divided into two groups. If Q equals 2, in contrast, the three vehicles are regarded as a one group in the evaluation, so they can reduce the total travel cost more. So now we evaluate the Q against for run times, and the figure shows the mean run times. From the results, we conjecture that smaller Q requires more run times. Second, we observe the behavior of IP solvers with respect to the parameter theta used in the branching and bound procedure. In branch and bound, if both the upper bound and lower bound are close enough, the solver stops. Three figures show travel cost, resulted gaps by solvers, and runtimes. So we can see that if we set theta to 0.01 or 0.1, the computed result seems to be almost optimal. In addition, computational times are not so large. We conclude that we can use the IP solver to find feasible solutions. However, it still takes a long time to build IP instances. Therefore, applications of IP solvers are still limited. We therefore start to develop heuristic solvers for this problem class. Our idea is to split vehicles into small groups using graph matching as follows. First, we fix some paths of a vehicle of the group. Second, we build other paths to cooperate with a fixed path. For example, for this request, we decide to cooperate with a blue or red based on the shortest paths. Last, we divide problems using scores based on the pairwise evaluation using shortest paths. In comparison, we prepare three variants of the third steps: the greedy, one matching, and B matching. The above chart shows the ratio of total travel cost, and the below one shows run times. The dotted line shows the total travel cost of the shortest paths, and the red line shows the optimal total travel costs obtained by IP solvers only for small instances. From experiments, we know that simple solver can solve much large instances than the IP solver. However, in the current status, the standard heuristic search techniques are still underdeveloped. In conclusion, we are now studying the path planning problem class for heterogeneous vehicle types. Our future work is to develop more heuristic solvers. Thank you for listening.
Hello everyone, I'm Gilles Pesan from Polytechnique Montreal in Canada. This is joint work with Behruz Webeki, doing a postdoc with me in Montreal, and Claude Guy-Quimper from Laval University. So this talk is about solving some AI planning problems using a standard constraint programming approach with nothing specific to planning, and in particular how some generic combinatorial search heuristics developed for CP are key here for our approach to be effective. So I'll first give you a quick background on AI planning, on constraint programming. Then we'll see, using a well-known planning domain, how one can model it in CP. Then how we explore the search space defined by that model. We'll have a look at some experimental results and conclude with some remarks. So, some background. So we're interested in classical AI planning problems. Well-known example is blocks world. So you have a number of blocks here, A, B, C, set on a table in a certain configuration. You have an initial state of the world, shown here on the left, and you want to reach your goal state, so another arrangement of the blocks shown on the right. To reach that goal, you have some actions that you can perform on those objects. So you can stack or unstack blocks, or pick them up from the table, or put them down on the table. You don't know how many actions you'll need to execute that plan, how many steps there are. And in the planning community, they're interested in designing domain-independent planners. That is a planner that will be just as good for blocks world as any other planning problem, so nothing specific to the blocks world problem. And in our case, we can see what we're proposing as a planning-independent approach. So we're using some out-of-the-box CP constructs to solve planning problems. There's nothing specifically developed for planning. How about constraint programming? So you model your problem, you define some variables, each taking its value from a finite domain of values. On those variables, you impose some constraints, and the CP has a rich set of constraints beyond just arithmetic constraints, for example. And behind each constraint, there are sophisticated inference algorithms to help you solve the problem. You solve a combinatorial problem by tree search. At each search tree node, you perform some domain filtering. That is, you remove from the domain of variables values that cannot possibly lead to solution. And of course, you branch as well. And the effectiveness of your approach can be quite dependent in general on the quality of your model and the quality of your branching heuristic. So you have to write good models and use good branching heuristics to solve your problem. Among those, that rich set of constraints that CP provides, one that will be very useful here is the regular constraint. So it's based on automata. So given a sequence of variables x1 to xk and an automata a, it will impose that the sequence of values taken by those variables spells out a word that is recognized by the automaton. And there's a cost variant of that constraint, cost regular, where you're associating costs to each transition of your automaton. And cost variable z is equal to the sum of those costs. So using CP for AI planning is not new. Typically, you fix the plan length and look for plans of that length. You use constraints such as regular. As early as 2006, there's been proposals for that. But typically, you use simple combinatorial search heuristics. So what's new here? We use the cost version of regular as well. For a given plan in an object, we will map the set of all actions to a reduced set that are relevant to that object. We'll see an example of that soon. And especially, so we will be using combinatorial search heuristics that are much more effective while still being planning independent. So again, our aim here is just to use good old CP, nothing specific to AI planning. So how do we model a classical AI planning problem in CP? Consider the well-known floor tile planning problem. So you have a tiled floor. Some of those tiles need to be painted of a particular color. And you have a set of robots on that floor. They can move around, they can paint tiles, and they can change the color that they use to paint the tiles. So here you have 15 tiles. The dots on some of the tiles indicate the color that you need to paint them. And you see two robots whose color indicates the color they hold. The actions have different costs. And so here the planning objects whose state is affected by the actions are the robots and the tiles. So the first step is to define the variables of our CP model. We simply define one variable per plan step. Each variable takes its value from this set of all possible actions. There are quite a few here. So there are as many as the number of robots times number of colors plus 6 times the number of tiles. Second step, we need to add constraints to our problem. So for each planning object, we define the action mapping and a constraint to indicate which action is possible given the current state of the world and how that state is changed by the action. For example, for each tile, here's the tile automaton. So for a given tile, there are only 3 states. It is clear, occupied, or painted. And we dramatically reduce the number of relevant actions here. We can move to a tile, move away from it, you can paint it, and all other actions are irrelevant to that tile and are mapped to an other action. And we post a regular constraint on the sequence of variables using that automaton. For each robot, I'm not expecting you to read that automaton. It's quite larger and actually just part of it here. The states represent where the robot is at a given point and the color it's holding. We still map to relevant actions, but there are still quite a few. So basically the irrelevant ones for a given robot are the actions about the other robots. So we map set of all actions to that reduced set, and we use here a cost regular version. So we use the automaton to specify which actions are possible given the current state, but also include the cost of these actions on the transitions in the automaton. And there's a variable z sub r for robot r that represents the sum of these costs. Finally, step 3, you define the objective you want to minimize. Here we want to minimize the cost of the plan, so we minimize the sum over all robots of those z sub r variables. So collectively, the automata for planning objects provide a factored representation of the world. Consider, for example, the partial current state where robot R is on tile T with paint color white. You've got 3 automata represented here, one for tile T prime, which lies above tile T. So that's you have left below the automaton for tile T, and on the right, the automaton for robot R. In green, you have the current state of each planning object. So T prime is clear, T is occupied, and robot is at location T with holding color white. Suppose we're considering next action being moving up, so robot R moving up to T prime. That can only take place if that action is valid in every automaton. So it corresponds to a move to for tile T prime, a move away from for tile T, and a move up for the robot automaton. Those are the orange actions, and then you move to these current states. And then if you want to apply paint down, so the robot R painting the tile below, tile T, that's a no up, that's an other action for T prime. Tile T moves to painted, and these are the current states. But what's really going on inside each of these regular constraints here? Well, the automaton is used to build a layer graph. You basically unfold the automaton into as many layers as there are steps in the fixed length plan that you're considering. So here would be for automaton T. So that's what we've done here. And but because it needs to finish for a valid plan to be that tile T needs to be painted, in the last layer only the painted state is valid. The others will not correspond to a valid plan from the perspective that tile T. So we can clean up, and that's what happens in those regular constraints. Now, this is not something that's going on particularly for planning. It's just in general what the algorithm does inside that constraint. And now every arc left belongs to a valid solution to that constraint. In fact, every path from the first layer to the last layer is in one-to-one correspondence with a valid solution to the constraint. From this, what can we get? We can do some domain filtering that I mentioned before. So for example, we see that because in the second to last layer of actions, there's no move to action, that can be filtered out of the domain of possible actions in the third step of that plan. And in fact, we see that it makes sense. You can't, if you're moving to tile T, then you can't possibly paint it in the next step. So now how do we search over the combinatorial space that's been defined by our CP model for our AI planning problem? So as I said before, we're solving fixed length plans. We do something very simple. We solve models of increasing length. So we start from some trivial, really, lower bound L min. As I said, we don't want to inject really any smart planning knowledge about the lower bound on plan length. We stop looking for plans of increasing length once we've established that there cannot be better ones further down. And when we solve our model for a given length L, we also include a timeout to possibly interrupt and move on to the next length. So what are those combinatorial search heuristics that really make a difference here? They're based on counting solutions. So here again is the layered graph that we maintain for each regular constraint. And we can also store some information about the number of incoming paths and number of outgoing paths in each node. That's what you're seeing here. And that information is being used to choose the next variable to fix, to branch on, and the value to give to it. Just to give you a bit of an idea, so for example, if we look at the red arc here, that corresponds to a move from action, and the second step of our plan, we can multiply the number of incoming paths, this is 1 here, to the number of outgoing paths, 2. So to get that there are 2 solutions here in that to that constraint that use the move from action step 2. And you can observe from that information that a move from action as a second action is twice as frequent as a move to or paint action in valid plans with respect to that particular regular constraint. So you use that frequency information to decide what to branch on. And what we've observed is that this tends to correspond to making smart choices of actions to try first. For example, in the floor tile planning domain, it could correspond to painting the tile currently above a robot if he's got the right color and he's in the right place. Or moving one robot out of the way before having another paint a tile. So all these actions make sense and they're selected as actions to try first automatically. And that's what we find quite interesting, without any planning knowledge being added here. I'll refer you to the paper for the experimental results on 3 different planning domains. But to summarize them, in the first experiment, we confirmed that counting-based search finds plans for many more instances than other common search heuristics in CP. And in the second experiment, we showed that on some planning domains, we can produce plans which are comparable to those from the state-of-the-art planner fast downward stone soup. So to conclude, I think the takeaway message is that you can build an effective CP approach to classical AI problems without injecting planning knowledge. What really makes a difference and here is using counting-based search as a combinatorial search heuristic. We observe that most of the computation time is wasted looking for plans at infeasible plan lengths, and that once we're at a feasible plan length, often very, very quickly we find a good plan. So we'd like to, as follow-up work, really look into counting-based search for planning, analyze more deeply its behavior and seeing how it relates to existing planning heuristics. We'd like to see how our approach performs if instead we start with a good heuristic to find a feasible plan length, and having an alternative modeling language for AI planning in terms of automata and action mappings would make it much easier to apply CP to such problems. Thank you.
Hello everyone, my name is Lukáš Hrpa and it's my pleasure to give a talk about planning in zero-sum games. So this is a joint work with my colleagues Pavel Rytíř and Rostya Horčík. So in real-world environments it might be the case that there are some other agents with conflicting goals, so such that they are competing for customers or for resources. So this means that generated plans should be optimized for strategies of these other adversary agents. So to do so, we can leverage game theoretic methods such as the well-known double oracle algorithms, so that can generate randomized strategy for the agent. So, and in our previous work, so we combined automated planning with double oracle. So the problem is that the plane combination didn't really scale well. So in this talk, so that I will be talking about heuristic methods that improve the scalability. So I believe I don't really have to introduce planning, so that here we consider durative actions, those that are defined in PDDL 2.1. We consider action costs and soft goals, so which means that these goals don't have to be achieved, but for each of the soft goals which has not been achieved, so there is some penalty given to the agent. So in zero-sum games, so that whatever agent gains, the competitor loses, and vice versa. So the thing is, in our case, if an agent achieves a soft goal, so the competitor can no longer achieve the same soft goal, and of course vice versa. So, and also the reward for achieving a given soft goal is the same for both the agent and the competitor. So to give you an example, we define a resource hunting domain where there are two teams of UAVs, so the blue one and the red one, that they are competing for these resources, the green ones. So to make it slightly more challenging, so that the resources can be collected by specific sensors that the UAVs can carry. So that, for instance, here this UAV with sensor 3 can collect these resources. So some resources require two sensors to be collected, which sometimes can be done by a single UAV, but sometimes so that there have to be two UAVs that have to collect the resource. And once a resource is collected, so the resource is gone. Now we will leverage the well-known double oracle algorithm, so one of the best known algorithms in game theory. So that the double oracle is based on solving restricted games, so that the restricted game has, let's say, several strategies, or several, in our case, several plans, so for each of the agent, and by solving the restricted game we are assigning optimal probabilities for executing each of the plan. So when we do this, so we try to compute a best response, or any response which improves the result, which improves the player strategy. So, and if we can, so that we just add that strategy or that plan into the restricted game, so then we try to compute best response for the other player, and we iterate until we are no longer able to improve the result. So, to give a planning perspective, so that we have what we call critical facts. So that critical fact is present in the initial state. It is required by some agent actions, but that fact can be deleted by some competitors' actions, and however it cannot be achieved by agent's action. So for instance, so that the availability of the resource is a critical fact, so that so it is required by the collect actions, but the competitor can collect it before and delete the fact which can no longer be re-achieved. So, and the actions, the agent's action required in critical fact are called critical actions, and similarly, competitor actions deleting a critical fact are called adversary actions. So the main idea is to plan agent's critical actions before the adversary action. So in other words, application times of adversary actions are setting deadlines for agent's critical actions. So, and since we know competitors' randomized strategies from double oracle, which are in form of a set of plans, each with a given probability for execution, so that we can determine the cost of agents' critical actions. So, such that for those situations, so we are missing a given deadline which is set by a given plan, so with a given probability, so we will be penalized for failing to achieve a given soft goal, so that which is, for instance, the value m, right? And of course, this is the sum across all the planners, across all the plans. Also, we are considering the tie situations in which we are planning our critical actions at the same time as the adversary ones, and in such a case, so we have a 50% chance to succeed. So, just starting with our heuristic approaches, that one is motivated by the well-known Hmax heuristic, so, and we leverage that concept to develop an algorithm that estimates earliest action application time. So that this is really similar to Hmax, so that we have for initial facts we have time equals 0. So, and for action, so we are just maximizing across the time of the facts in action precondition. So here we relax at end precondition, so because otherwise it will be much more complicated, yet it will not compromise the property of the estimation that actually is let's say lower bound of the actual application or earliest possible application time. And for fact, so that we just choose the minimum of the times of the facts achieved by action effects. So this algorithm can help us with pruning those critical actions whose earliest application time is after all the deadlines. So therefore, such a critical action has no chance to succeed, and hence we can prune it out. So another technique actually selects and gives some partial order to critical action, so that the planner doesn't really have to decide which critical action and in which order they should be applied. So therefore the planner is just filling the gaps in between. So for that, so we just adapt the previous algorithm by considering some actions with fixed application time, and we also considered some effects of these actions, so that we know that certain facts will be true at some time, and so on. So the details are given in the paper. So here we are considering so-called clusters of critical actions, where each cluster corresponds to a particular soft goal. So in other words, these clusters are in fact disjunctive action landmarks for a given soft goal. So, and what we do iteratively, we are selecting a critical actions from not yet considered cluster. The time of the critical action is not estimated to be after the latest deadline, and with, let's say, all the possibilities in a given step, it yields a minimum cost of the plan. So, and the cost is estimated from the time estimates or the application time estimates of critical actions. So, and we simply continue until we can select these actions. So, and at the end, we just ordered selected actions that are, let's say, dependent on each other. So, for instance, actions that are using the same UAV, so they can't really be executed in parallel. So now to improve our selection and ordering techniques, so we leverage simulated annealing, and we considered two types of operation. So one is changing order of critical actions. So for those critical actions that actually have defined the ordering constraint, or we can substitute a different critical action for the action from the same cluster. So, and the objective function is to minimize the estimated cost of the plan, which is estimated by the same way as before. Now, so we encoded the resource hunting domain as type strips, so that the details are given in the paper, so that we actually encoded time as like timestamp objects. And we considered two types of scenarios, so that we called middle and diagonal simply as resources are placed. So we use an optimal planner, which uses a potential heuristics, and a satisficing planner, the well-known llama planner. So, and for, let's say, each planning episode, each computational best response, the timeout is half an hour. So that for the optimal planner, so the results are actually the optimal values for the classical approach, which is just the plain combination of planning and double oracle, so that we can see that player 1 has slight advantage, so that it can collect in average slightly more than player 2. So with the pruning heuristic, so that the optimality is not compromised, because we are just pruning critical actions that are useless. So of course the optimality is compromised with the using of ordering heuristic or the local search approach, even though the optimal planner is used. But what you can see for the local search approach, actually the values are quite close to the optimal ones. And so if we go to the results where we use satisficing planner, so we can see that we can scale beyond 3 UAVs up to 8. And if we just look at the results of the local search, so that even though we were not really able to compute the equilibrium, so as a rule of thumb, so that since these scenarios are let's say proportionally scaled, so therefore if the values of player 1 and player 2 are close to each other, so that we believe that they are close to equilibrium. So that this is what you can see in most of the values for the local search. But I mean, sometimes there are huge discrepancies, and this is the most profound example, so where the player 1 collected all the resources, right? And I mean, the reason for that is not just that the heuristic doesn't give a perfect estimate, but also sometimes when the satisficing planner is used, that the plans are not of the best quality. So, and in this case, it simply was a poor quality plan for player 2, which somehow couldn't be improved, which simply led to this result. So, I mean, in summary, so the good news that our heuristic works and scale beyond the classical approach, because it really doesn't scale beyond 3 UAVs, so at least we could do for 8. And with local search heuristics, so the results are of reasonable quality. So just to mention, so you can see in the paper that the runtimes are in order of thousands of seconds, just to just compute the, let's say, whole game. And it depends on the number of double oracle iterations, and also what I would say, complexity of planning tasks. So, I mean, typically the planning tasks are quite hard for the planner. So if really we need to calculate, generate plans that are close to optimum. So, and as I said, so sometimes these strange results are caused by generation of very suboptimal plans. Thank you for your attention.
Hello everybody, this is Mohammed Abdulaziz. I'm from Technical University of Munich. Today I'll be talking about joint work with Dominic Berger, who was one of my bachelor students. In particular, this is about a new algorithm to compute upper bounds on plan lengths. So in this work we consider computing a quantity called the recurrence diameter of state spaces of planning problems, and using that to compute upper bounds on plan length. So first of all, I want to define what a recurrence diameter is. So given a directed graph, the recurrence diameter is the length of the longest path in the state space in that directed graph that does not traverse the same vertex twice. So it is the longest path, the longest path that only traverses the same states. The complexity of computing the recurrence diameter for an explicitly represented directed graph is NP hard. So that's a problem. So it can have bad running time for practical algorithms. So in this work we explore how to compute the recurrence diameter for planning problem state spaces while and how to do that in a practically useful way. So the reason we do that is that we need computing recurrence diameters would improve if we have a practical way to compute recurrence diameters that can improve the upper bounds a lot on plan lengths, and this in turn would improve the performance of set-based planning algorithms that use these upper bounds on plan lengths, either to find plans more quickly or to prove that a certain planning problem does not admit a solution. So the challenge for this, the challenge is not that the running time, that the complexity of computing the recurrence diameter is only NP hard. It is indeed non-deterministic exponential hard for succinct directed graphs like state space of strip spanning problems. So what that means is that computing the recurrence diameter can actually take a doubly exponential worst case running time in the size of the given planning problem. So we solve that challenge by two contributions basically. The first one is we devise a data encoding into SMT formulae, and we basically encode the question of is a certain number the recurrence diameter of a planning problem into a small SMT formula. So just to be quick here, so the only previous encodings for recurrence diameter, the first one was invented by Alain Biere since 1999 when he invented bounded model checking, and since then it didn't really improve much. And the problem of that encoding is that it builds the entire state space and then produces a formula whose size is quadratic in the size of the entire state space, so it can be exponentially bigger than the given problem. Our encoding has the advantage that the formula can actually be only quadratic in the size of the given planning problem, so the quadratic in the size of the factored representation, and thus it can be exponentially smaller than the formulae by Biere. Another contribution is that we devise a method that shows how to practically compute the recurrence diameter and only for projections that are small, for projections of planning problems that are small, and for other projections that are bigger, we compute other bounds other than the recurrence diameter, and then we show how to compose these bounds for a given planning problem into a bound on the whole problem. So a given planning problem is divided into abstractions. Small abstractions we compute recurrence diameter, bigger ones we compute other bounds. So as you see here in the experiments, the bounds computed when the recurrence diameter is involved are much tighter than the ones when it's not, as shown in the left figure. But the problem is that bounds computed with the recurrence diameter take longer than bounds computed with other algorithms. But as shown on the right plot, the overall running time of planning, including the running time for computing the upper bounds, still is much better when you have when you use the recurrence limiter, because the bounds are very tight that it eventually pays off. Thank you very much. If you have any questions, please email me.